congratulations for showing up tonight. I thank you very much. Let's go to the next slide. So this is the point where we ask if we have any visitors tonight, and I think we have at least one. And I'm going to come around, and I'd like for you to introduce yourself and how you came to find the club.
My name is Jean Walker, and I am associated with the Lone Star Observatory, a group of us from the Dallas-Fort Worth area, but we have a telescope and observatory up in Oklahoma. And I wanted to learn more about your group and start coming to meetings and be associated with this group. So I'm glad to be here. Thank you.
Thank you, Jean. Thank you, Jean. Any other visitors? Fantastic. Let's go to the next slide. So these are our new members since our last meeting. Are any of those people here tonight? Oh. So who are you? Please introduce yourself and how you came to find the club.
I'm Rob Porter. I've been retired for about 5 years. My wife wanted me out of the house at night. And I just found the association on the web, on the internet, and YouTube. And I just got a Apertura 88 Dob about 4 months ago. And that's about it.
All right. Thank you, Robert. I see Fred's name's up here. Fred's one of the folks from the Cross Plains area that joined the club. Okay, let's go to the next slide. Oh, hey, we have another guy. Another new member. So please introduce yourself again and how you found the club.
I'm Tom Schneider, and I've lived in Fort Worth since 1988. And I've always kind of been interested in astronomy. So I found the club, and I joined the club, and I drove out to the site, and oh my God, I've got so many questions. We go to Colorado every summer for vacation, and it's just amazing. And I remember looking up and trying to see one satellite, and now you can see 4 or 5 at the same time. It's incredible up there. But to think that there's a Bortle 2 so close, I mean, it's really exciting. I recently bought a Skywatcher Heritage GTI 150, 750, and I need some advice on eyepieces. And so far I've seen the cloud bands on Jupiter and Venus's crescent. I was looking at the moon the other night, and it was almost blinding. So anyway, I'm really interested and excited about this opportunity to meet with you guys and learn what you know. I came here in the January meeting, and I thought my head was going to explode. So.
Well, I'm very happy you returned. Okay, let's go to the next slide. Okay, so the club was formed by Charlie Mary Noble some 76 years ago, about when it was time for her to branch out. She had already formed an astronomy club for children, and she decided it was time to form a club for adults. So she started the club in 1949, and man, have we evolved since then. We're now a nonprofit club where our mission, I guess I should say, is to educate and provide outreach to the public. And to do that, we concentrate primarily on star parties and educational activities at schools. But the club also offers to new members and old members the same expertise in which we would answer your questions, we'll give you advice, and help you through your astronomy journey. And I'm sure there's 20 people here to give you advice on what eyepieces to get for your scope. So let's go to the next slide. So in terms of our resources, if you have a scope, you want to get into some dark skies, and the two items listed first are our answer to that. The first one is the club-owned Rising Star Observing Area.
Recording in progress.
In case that question was on your mind. So it's Rising Star Observing Area. It's in Eastland County, and provide bortle 2 skies, very dark, especially when you consider the DFW light pollution that we deal with. The other observatory that we have access to is the Thompson Observatory.
There's supposed to be audio?
Southwestern Adventist
I can hear now.
University in Keene, Texas.
Okay, yeah, I'm hearing you, Richard.
Oh, and am I going to be introduced or should I just start?
So we're having technical issues here in the classroom. So we're going to mute the lines because we can hear the chit chat and at very loud decibels.
So there'll be an introduction.
Oh, thank you. So we also have club telescopes. Most of our club telescopes are at Rising Star, where you can go into the 40-foot container and check them out onto the field and use them. But we do have a loaner program that you can check them out and take them home and use them for an extended period of time to make sure that that's the right scope for you prior to making that purchase. And then we also have additional resources through our membership handbook and our online resources, which we'll get to in the next slide. And our first online resource is our website. It's the one-stop shop for finding out about the club, what our resources are, what star parties we have available, and how you might be able to request a star party. We also have a page that offers our merchandise, so you can find how to get a coffee cup, a t-shirt, or a hoodie. So you need to check that out. We do have a presence on social media, starting with our Facebook page, where we explain to the public, or provide the public, I should say, information about the club and upcoming astronomical events, as well as star parties that they may want to participate at. Our YouTube page is really a collection of videos that we have of meetings and virtual star parties that the club has presented. And if you think a video collection of meetings is perhaps a little dry, boring, I suggest you just skip over to the technical presentations that are given, because we've had great technical presentations over the last 2 or 3 years. So that's a very valuable resource. And then the other two online items we have are email chat groups. The Fort Worth Maine is where the club members get on board and ask questions to other folks or advice on different items, as well as we keep the membership up to date on club business. And then the APIG-SIG is a special interest group for astrophotography. And here they look at emerging technologies that will improve imaging, but they also cater to the newbies, the folks that are just getting into astrophotography, and where they go over the basics and essentially drop back to square zero and start working their way back up. So it's a good reminder for the experts that have been involved in astrophotography for a long time, but it also helps the new people get started. All right, next slide.
So, knock knock. Interrupting astrophysicist. Black holes. Sorry, that's as good as I can do as far as jokes are concerned. So who I want to introduce tonight is Dr. Richard Anantua. He actually collaborates with the Event Horizon Telescope, and he is part of an outreach program that, from what I understand, he can probably explain this to you a little bit better, actually brought the science of the Event Horizon Telescope to Texas, San Antonio, University of Texas at San Antonio. So, Dr. Anantua, it's all yours.
All right, so it's great to be unmuted and here. I'm Richard Anantua. As Bill introduced me, I'm a fairly recent assistant professor at the University of Texas at San Antonio, and even more recently, adjunct professor at Rice. So whether you want to go down the I-35 or I-45, I'm very conveniently in the state. And I am going to be giving you a glimpse into what it takes to find the first images of supermassive black holes. So these are direct glimpses into the horizon of black holes, and these are two images because we have, since 2019, been able to reach this level of precision to become what are now the most highly resolved images in astronomy, to be able to probe scales that are a few tenths of microarc seconds, or the amount of precision you need to read a credit card on the moon. So with these images, we've entered into a completely new era in astronomy, where we are now able to see directly into the horizon scale. And what it takes is often done in a theoretical framework, but it's also a lot of observational astronomy. So I sit in the middle ground between the theory that Einstein gave us, which tells us how space and time warp in the presence of strong gravity, and the radio astronomy observational techniques, which have been tried and true for generations. So an outline into how the sausage or the glowing donut is made is starting with an introduction to the Event Horizon Telescope, some terminology and definitions that we use in this trade, the process of turning the world into a collecting dish. So if some of you are around 6 years ago, you might remember some of the media and fanfare around this type of work. So this was really a truly fundamental landmark in astronomy, and it happened. It was available to the world 6 years ago, but it was a long process in building up the array to the point where we were confident in what was produced. This story in particular is relevant to Texas, as I brought down the first Event Horizon Telescope group in the state. So I finished my postdoc at the Harvard-Smithsonian Center for Astrophysics late 2021, and I came down here in 2022. And I am mostly on the theory side of this, but I connected to, and I'll show you some of the nuts and bolts of the mathematical calculations that go into simulations that verify what we're seeing has some well understood physical basis in plasma physics. So first I will show an exercise in starting from before the 2022 Sagittarius A-star was imaged, how one from the ground up can have a first principles image that looks somewhat like the data. And then I'll be going into some of the retrodictions of after the M87 image came out, what are some of the modeling steps that will make the synthetic images look a bit more like the observations. So that entails adding this antiparticle to the electron known as the positron into the simulation pipelines. And then I'll show some of the highlights of what the historic results of Event Horizon Telescope means to the world. So the fact that the images are now iconic helps in the sense that it gets people engaged into having more hands on deck for solving the future mysteries that we're certainly bound to encounter. And now, after this has been done for M87, we had a very surprising result in 2022 after this M87 image. So the M87 image taken in total intensity and with polarized light, which is this structure on top of the total intensity image here, it looked how we expected it to look based on how the large-scale jet in M87 was pointing at a small angle to our line of sight. So we expected to see a disk of inflowing material roughly in this orientation. However, for the 2022 result in Sagittarius A star, here's our vantage point looking into where Sagittarius A star should be. So if we extrapolate what happens when we see a outflow pointing towards our line of sight and we expect the disk to be perpendicular to this, we had a very surprising result when we saw the image of Sagittarius A star in that it also looked face on. So even before the surprising result, some of the simulations could tell us what are some of the features we'd expect, including some of these bright hotspots that are equally distributed across this ring, rather than the very one-sided features that we saw in M87. So the Sagittarius A star polarization paper also showed a similar spiral pattern, this time across more of the ring that we can see of polarization. So this is only the start. Only 2 of the hundreds of billions of supermassive black holes thought to be in the galaxy have been imaged thus far. So we could get even closer with higher frequency imaging at 345 gigahertz in the future, but we can also look at different sources. 3C279 and OJ287 come to mind. And of course, we have images over time. So the next logical step is to make the first black hole movies. So we need to discuss some of the terminology and definitions that are relevant to this in order to start to understand some of the mathematics that goes behind this. And to this end, we have active galactic nuclei, which are emitting regions around the supermassive black hole that appear as a discrete source. Accretion disks are typically magnetized inflowing plasma that are gravitationally bound to a central object like a supermassive black hole. So here's NGC 7742, an example of this type of phenomenon. Magnetically arrested accretion disks are actually inhibited from inflowing like a normal flow onto sink because they have such strong magnetic fields in the plasma that they're bringing in that the fields themselves cause the disk to be arrested. So if you ever try to jam too much magnetic field into a small region, you get this type of phenomenon, and black holes are no different. So, of course, if we have magnetically arrested disk simulations, the next logical step is standard normal evolution, or SANE, which is not so highly magnetized that it can flow as normal. We have Stokes parameters that determine the amount of intensity and polarization that you're seeing. So the Stokes I parameter is the total intensity, and that's the image that you see without the linear structure that we added on top of it. But we can also add some of the polarization structure, which tends to follow magnetic field lines or have a definite relationship with the magnetic field structure. And these linear polarizations you could think of as what you would see if you were to look at a polarized glasses at 230 gigahertz frequency and be able to do the radio astronomy in your brain. You would actually be able to pick out some preferred orientations of the photons that are coming out of the structure that you're looking at. Circular polarization V is also very informative. It's the remaining polarization that is polarized in the sense that it corkscrews one way or another. A jet is a relativistic polar outflow that is part of about 10% of AGN supermassive black holes. And part of using these images to understand the theory behind the astronomical observations is to test a model of relativistic jets, actually from my PhD advisor, Roger Blanford, known as the Blanford-Naik jet mechanism, which is how vertical magnetic flux accreting onto a black hole can actually interplay with the strong gravity around the rotating black hole to twist up and add some energy in the jet so that the energy can be released to high energy particles that ultimately source the very bright and energetic flows that we sometimes see coming out of the active galactic nuclei and extending to a appreciable fraction of the entire length of the galaxy. So whether this picture holds is something that we can actually test with our theoretical models and simulations. Synchrotron radiation is the type of radiation that we will be seeing from these jet structures and also at other places in the jet accretion flow system due to gyrating electrons or positrons around magnetic fields. So when I say near horizon, here's a sense of where we're headed. The constellation Virgo is at 12 hours right ascension and 13 degrees declination. And it's our best studied cluster of galaxies. The supermassive black hole with the largest angular width in the sky, aside from the one in our own galaxy, resides in the Virgo cluster, roughly 2,000 times the distance from the intergalactic center. And this galaxy, known as M87, that houses this black hole, is first seen as a curious straight ray, but is seen at many different frequencies all the way down to the edge of the event horizon. So these are the latest observations of M87, going all the way back from that large-scale jet observed in 1918, all the way down to M87, incidentally observed first in 2019, and now in polarized light. So with these observations, the insiders that made it know that this is no small feat. So in order to make such an image, it's required to increase the resolution limit to the point where we can see the scales that we were describing before. So the scales to read a credit card on the moon or to resolve an atom at arm's length. In order to do this, it turns out that in astronomy, the scales that we need to resolve in a particular wavelength are related to the wavelength, but they're inversely proportional to the size of the aperture of the instrument. So if we want to resolve exceedingly small angular scales, like the ones that I was describing, it's necessary to make the aperture size enormous if we want to do that at a fixed frequency, like 230 gigahertz. So we actually turn the Earth into a collecting dish. Now, you might ask, how does that work? We can't, due to perhaps environmental regulations, put a receiver at every square inch of the Earth's surface. So this actually is accomplished by choosing some strategic locations. As you can see, these are fairly spread out and they fill up the sky, especially when the Earth rotates, we get more coverage. So we call this coverage, in the parlance of radio interferometry, UV tracks. And this is a better coverage of the Earth than if we simply had one stationary receiver. So the rotation of the Earth allows us to see the source at more orientations relative to what we would if it were just sitting somewhere. And the measurements that are taken are correlated flux across baselines of different length. And when we have long baselines coupled together with short baselines, we could see how much correlated flux varies with the length of the baseline that we're measuring it on. And these types of patterns are what we use to collect data for both of these sources. And we first collected these data in 2017 with the entire EHT array. So as some astute observers might know, some of these telescopes were around earlier, like ALMA. Some of these telescopes were observing things in astronomy way before, but it became the EHT array able to have various different baselines where you can measure this correlated flux density with at many different times, and capable of doing this measurement only in 2017. So this array is sort of an emergent property. And the more we fill this space, which we call the UV space, with what we call these visibility amplitudes versus baseline, or with the correlated flux density for baseline on this UV configuration, the better we can resolve what type of image it is by the mathematics of a Fourier transform. So how we do this in the other direction, namely from first principles, try to build these types of structures up. This is what type of science I hope to bring to the state with the first Event Horizon Telescope group in the state at UTSA. And some of the stars of this operation are my postdoc Brandon Kurd, who got his PhD at Harvard in 2022. He came down to do some of the cutting edge simulation work that goes into this type of reverse engineering analysis that my group specializing in. My first PhD student, Joaquin Duran, who's now in the middle of his PhD, he helps with some of these applications of simulation modeling to various different sources. My new PhD student, Nate Lujan, who is he spent quite a long time in the military in San Antonio, and he's working on various applications of dark matter. So he's taking a different tack for understanding dark structures like Segway-1, also in collaboration with Carl Gebhardt of UT Austin. And Haley West, my master's student, and Haley is extremely adept at data analysis and making some of these images from the simulations. So with this group, we have made models that, from first principles, reproduce in magnetically arrested disk cases and in standard and normal evolution cases, or in cases in between, what phenomenology we expect to be underlying these astronomical images. So some of the highlights of what we're doing: we are the first Event Horizon Telescope group in Texas. So we're the first group that has the data from near horizon signatures of plasma physics. We pioneered and developed particular models like the critical beta turbulent heating model that goes into some of the analysis to help understand what is causing the plasma around these black holes to be heated to the billions of degrees that they need to radiate the amount that they do. And we also add other particles than are traditionally added in these analyses. So adding positron physics to the pipeline in M87 is a work that you can look at monthly notices of the Royal Academy of Sciences, or sorry, the Royal Astronomical Society, and see this paper that describes this type of modeling and what the positrons help us do in order to understand the difference between the accretion states around the black hole. So the pipeline that we created, or that we're still working on, I coined as observing JAB simulations, as you need an acronym to be successful in this field. So we start out with a general relativistic magnetohydrodynamic simulation or semi-analytic model of a jet or outflow, accretion flow, or a black hole. And then the modeling step that's between the simulation and the observation is to convert the GRMHD variables into prescriptions for the astrophysical radiative processes like emission, absorption, polarization, with different models for particle acceleration and dissipation to try to model what physics is dominant in the particular source you're looking at. And then we try to optimize our models to best fit the sources that we're viewing. So these sources are EHT targets like Sagittarius A star, which is the first source that I studied, even though it was the second source that I imaged. And this is in a paper I'm going to be calling paper 1 from now on, when I was a postdoc at Berkeley before I started my Harvard postdoc. So this work was in collaboration with Sean Ressler and Elliot Quartert. And we found that using a wide parameter space of different phenomenologies like turbulent heating or heating from magnetic energy, we could reproduce a wide range of possible morphologies, but the best morphology came from certain turbulent heating models with a high value of the plasma beta. This is the critical beta parameter in that model. And this model had the best size, asymmetry, spectrum, and variability that matched the observations the best. And the other models clustered in other parts of parameter space. We did the same analysis, but now adding positrons to M87 and some new models. And we have this monthly notices of the Royal Astronomical Society paper, Ananto et al. 2024, where with other collaborators, we find that the type of accretion flow, whether it's sane, standard normal evolution, or whether it's magnetically arrested disk, matters a lot, especially when positrons could be part of the emission maps. So we found that sometimes the observations favor standard normal evolution with particular observations that don't resolve that do resolve the local polarization structure, but when you don't resolve it, the MADs are preferred. So the first source that I studied is Sagittarius A star, and there was an entire observational campaign dedicated to it. So where we're going, we're in the Milky Way galaxy, approximately 100 kilolight year in diameter, home to approximately 100 billion stars, and Earth is about 8 kiloparsecs from the galactic center, but we actually need to go much closer in order to start seeing the phenomenon that are relevant to the Event Horizon Telescope. So if you go down to the inner parsec of the galactic center, and mind you, we're 8 kiloparsecs or 8,000 parsecs away, if we go down to the inner single parsec, we see the orbits of some stars that end up appearing very eccentric. And these stars, before we can see them through the Event Horizon Telescope, we can only infer what these stars would do. So we see stars that are interacting with some very sharp gravitational potential, but we couldn't see it before we had the observations by the Event Horizon Telescope. So we're right now looking at a black hole that is 410 millionths of a parsec. These are 100 kiloparsec scales. We're now looking at 410 millionths of a parsec, or a 7% of an astronomical unit at the galactic center. And we're trying to understand what are the phenomena that go into these very first images at this scale. So this was seen before by the gravity 4 very large telescopes in the infrared. But in the infrared, you couldn't resolve. You can only see the centroid moving, and you can only see some polarization directions in an unresolved blob like this one. However, with the Event Horizon Telescope, we actually see what goes on in here. And with our theoretical models, we can understand what type of physics might predominate. So let's take you back to Berkeley circa mid-2010s, when I was doing this analysis without the 2017 observations published yet. So this type of the type of data that was available was roughly symmetrized data from a pre or proto-EHT array, where we saw the correlated flux density along a few small number of baselines. And it was a mystery to see the visibility versus baseline pattern because so much of the space wasn't filled out. So one guess that was available, the simplest possible, was that the structure that we were looking at looked like a disk. In fact, a Gaussian 2D disk with a characteristic size that's given by the data that was available. So later data hinted that the structure looked more like this. So a lot more minima in this type of visibility versus baseline pattern, which would give us more structure like these non-point symmetric rings with accretion disks around them. So we had a couple of antiquated EHT measurements of the basic size, which we took to be about 37 micro seconds, and the basic structure with some asymmetry being revealed with what we call closure faces, which are some triangular analogs of the baseline invisibility calculation. So with that scant data, the image wasn't nearly as robust as the final image from the robust 2017 data. So the 2017 data that ended up being the final answer before we had access to this, it was a mystery. But this 2017 data was given by many different imaging algorithms or pipelines that use this data to actually get the final tracks in UV space for the array that's capable of seeing structure on this scale and using the interferometry to actually, in these many different methods, come up with the same answer. So these histograms find with different methods like DiffMap, EHT imaging, pioneered by Andrew Shale, Smiley, Themis with Avery Broderick. These different algorithms all use the same data and got roughly the same image, except for maybe 1% of the cases in yellow where it looked like a double source. But in all those cases, the size was consistent with one version of the previous, the size was consistent with the previous images that were inferred when we couldn't resolve the black hole. So the size of a black hole or the length scales are proportional to its mass, and that was a window into the astronomical properties of the black hole. So in order to actually reverse engineer that type of observation, we use radiative transfer, and radiative transfer tells us how to link source properties like the emission along the line of sight through this type of mathematical operation, namely line of sight integral. So here's the source, here's a property of it, and that information is encoded along the ray. But in astrophysics, our life is a little bit more complicated because we have, as we saw during observing job simulations, pipeline absorption, we have polarization, we have Faraday effects. So we have all these in a more complicated line of sight calculation with polarized radiative transfer, where we take the polarized emissivities that are the analogs of this for total intensity, but in polarized directions, and we subtract from it this matrix of the effects due to absorption in Faraday, both rotation and conversion of linear to circular polarization. So, this encodes some of the source properties through these functions. So we have some functions that depend on the plasma properties like the magnetic fields and the pressure of the relativistic particles through functions we can model, such as the number density of particles at particular energies gamma, where they're relativistic particles that could obey a thermal energy distribution, where there's an exponential cutoff at a particular temperature theta E of the electron energies or the particle energies. Or you can think of a power law distribution where this power law index controls how slowly the energies die at how slowly the number of particles dies at higher energy. So you can encode different models of what plasma physics is going on and tell us what the observer sees in the polarized signatures in these models. And we can compare the observed polarized data to the models. So how we make the models? So we look for an insight from solar physics. So Greg Howes pioneered a model of turbulent heating where he observed a particular behavior of the electron temperatures in the solar corona. So it turns out that the parameter beta, which is the gas to magnetic pressure ratio, is the key determinant in whether at a certain value of beta, the temperature of electrons is high versus relativistically cold or low. And the type of behavior that was found to be a good model for the sun is that if we have the temperature of the hot electrons at the low betas being high, and the temperature is cooling off at the high betas, as this exponential model is showing, then we can emulate how the sun tends to preferentially heat electrons at low beta and other ions preferentially over the electrons in high beta. So this is a parametric model controlled by this overall efficiency of how much of heating you're going to get, and also it's controlled by the plasma beta cutoff beta critical, where the electrons are preferentially heated at low beta and the ions at high beta. So that's one type of physics that's reminiscent of turbulent heating physics. How about a different type of mechanism? How about if the electrons are, instead of from turbulence, getting their energy from the conversion of magnetic to particle energy? So we can encapsulate that type of physics by the parameter beta E naught. If beta E is the beta analog for just the electron gas pressure, then PE over PB, setting that to a certain constant, is a model of the efficiency of conversion of magnetic energy into particle energy. And that can happen with mechanisms such as magnetic reconnection. So magnetic reconnection takes the energy in the magnetic fields and it siphons it off with a certain efficiency beta E naught into the particle energies. And you can do this to such an extent where you can feed in the magnetic energy to the particle energies and achieve equal partition. So E roughly equals strengths. You can have a magnetic bias model where you take the PE and then you relate that to powers of the magnetic pressure instead. So if you have a simple fall off of the magnetic pressure with powers of B, then you can have different simple geometric shapes that are either very, very narrowly collimated or very widely collimated, depending what power of P, B to the N you're using in this type of model. So armed with these models, we can have very different phenomenological pictures of what's really going on. So the true test is to compare these to the observations. So this is how these classes of models tend to cluster in parameter space. We have a cluster where you can reach this from the high F and beta critical beta parameter regime, or you can even reach this from the low constant beta E parameter regime in the different phenomenological model, where you can get the image size to be compact and asymmetric. So it also turns out that if you look at the spectrum produced by this model, up to maybe a little bit of a missing emission from some particles we can explain by other means, this spectrum roughly fits throughout a very wide range of the data. So that's a very different case than the models that we get when the F and beta crit values are low. In that case, it turns out that the profile we see is that of a outflow or coronal, which is a surrounding layer around the jet dominated emission profile. And the spectra tend to be steep because the particles tend to cool rapidly at large radii, contributing to these spectra. So if we have that model that is not compact and asymmetric, it doesn't fit the data on another account based on the spectrum. We also have another unphysical model that we found. And again, in the same simulation, we put in a model that has the physics of the particle energies derived from powers of the magnetic energy density. And at high powers, the emission that's contributing comes mostly from the equatorial inflow, where if you look closely, there's an equatorial inflow that's edge on, but you can actually see behind the disk due to relativistic lensing in the strong gravity of the black hole. But in this case, you only see one pulsing bright spot that's relatively stationary and a thick torus of a disk that it's being lensed. And the spectrum is quite bad in this shape. So the same simulation produced compact asymmetric images with bright spots that move in the first two cases I described, but that don't really move in the third case. And then in a case with the low end magnetic bias models, the outflow dominates the emission. So we have another model where the image morphology and the spectral characteristics are far off from the observations. So it turns out that the better the images are, the better the spectra are. Let's see if any other properties are singled out by this. So you can average out these models, and then you can basically see that they have roughly the pattern of a fixed envelope of emission and then some light around it. So if we look at this model, this seems to be the best from the standpoint of morphology and spectra. How about we go to variability? So the type of variability that we're getting is definitely on intraday scales. So in the units we measure time, this is about a day in the horizontal axis. So you see the different models correspond to very, very different variability properties. So it turns out that the type 1A images had the best variability, but the type 1A images that came from the high F and beta crypt models had even better and higher variability matching the data. There are models that look like those coronal alpha progressions with the low F and beta crit. They had some variability as well, but not on the smaller timescales that were more relevant. The models where the bright spot just sits on the equatorial plane had the worst variability. So these are some of the least physical models. Again, the same simulation has different phenomenology, and we can infer which phenomenology best measures the data. And the very extended outflows with the low-end magnetic bias models also failed on this variability test. So we basically picked out a model that the high F and beta crypt models are the best if you look at these models edge on. So what if you look at it face on? If you look at these models face on, we have a similar pattern where if you increase the values of F and beta crit, you end up with the most compact type of image. And this type of image best fits the data. So if we looked at this whole parameter space and we looked at the best models, the F and beta crit seem to be the best for the spectral properties, the variability properties, but there's still some uncertainty in what the orientation of the structure was. Are we looking straight down the rotation axis like this in the face-on image where we see the equatorial disk fully, or are we looking at it in different angles and up to edge on? If we look at it with different frequencies, like the gravity telescope infrared frequencies, what do we see? Well, if we change the inclination and the frequency, it turns out that the best images are for the intermediate frequencies, where we get to see in the infrared, there's still the existence of these hotspot features. But also there is some of this in the 230 gigahertz image as well, and it's not completely dominated by the gravitational lensing profile over here. So our best bet models doing this blindly look like this at 230 gigahertz, and if this is the right answer, coming from the zoo of models that we came out before, it turns out that this blind exercise was fairly useful at determining the hotspot properties that gravity saw at infrared frequencies and the EHT type of patterns that we see. So this is a key activity that we can do for other sources like M87. So if we want to observe M87, we have another feature, namely the large-scale relativistic jet in M87. And this jet has been observed in different polarizations for many years. So we see the polarization structure of the jet and the unresolved core at these ALMA observer frequencies, but on larger scales than the EHT. We've seen a history of these. So we get the turbulent features at the 43 gigahertz scales, and we get all the way down to seeing the ordered pattern of spiral electric vector polarization angles that indicate where the magnetic fields are oriented in the EHT scale M87 image. So how do we apply our methodology to this? So we can have a simulation library with models that are reminiscent of the critical data turbulent heating model, namely in the Event Horizon Telescope simulation library. So when this work was done, this is before we did the observing JAB simulations pipeline on it. So the Event Horizon Telescope was using a different model. They used the R beta model where, again, at a low beta, the ion to electron temperature ratio is low, and at high beta, the ion to electron temperature ratio is high. Notice that before the critical beta was in terms of the electron to total temperature ratio. So there were opposite patterns when beta is low and high, given the ratio flipped in this case. So using this model, you can test different black hole spins, and this black hole, namely, is attached to a jet, so it appears different. It turns out that the jet spin had a bigger effect than the other parameters. So if you look at these different spins, the extreme retrograde minus 0.94 dimensionless spin and the extreme prograde spins had the most bilateral asymmetry, whereas the spin zero cases, here you're talking about the MAD side, the spin zero cases were very roughly symmetric. So this tells us that the spin asymmetry is something that is more likely in the type of image that we got in M87, so it disfavored these spin zero cases. And also, the MAD patterns were favored on the left half more than the sane because the MAD had the more spiral shapes of the EVPA patterns than the sane, which were a little bit more perhaps radial or even azimuthal. So it turns out that the sane patterns of polarization were what precluded them, mostly in this analysis with this type of turbulent heating. Now, what was missing in this analysis is the effects of positrons. So positrons can be modeled if we include them in the post-processing, assuming total charge neutrality. And if you modify the radiative transfer coefficients that you saw in that matrix before, but now you add this positron fraction, we can see completely different effects. So to have a sense of what effects we're going to see, let's observe the semi-analytic model instead of the simulation, because you can make a semi-analytic model expose it to a larger range of scales than you can a simulation. And if we observe a semi-analytic model, first with no positrons, we see can reproduce some of the general flavor of the observations on the right. So in the semi-analytic model where we had, before relativistic beaming, a fairly axisymmetric jet, what we have when we add the relativistic effects that favor one orientation through this combination of B cross n hat, where n hat is the direction to the observer. If the helical field is rotating with different pitch angle, B cross n hat looks different on two sides of the jet. And we can see a bilateral asymmetry partly because of that. And also in our semi-analytical model, using a constant beta E model with a small value of the beta E parameter, we get a very core-brightened polarization profile that's similar to the observed jet of M87. So if we take this model and we now put in some general relativity and observe it close to the black hole, we can have positrons. And for this constant beta E model, for the lower value of the beta E, you can see that at total intensity, you don't see much difference. But when you look at the polarization signals, no positrons versus positrons, that has a quite different structure and also magnitude of the linear polarization. So here it goes up to 80-ish. Here it goes up to like maybe 50 something. So you get more linear polarization when you add the positrons. And you completely change the structure of the circular polarization from top to bottom when you add positrons. So this effect becomes even more pronounced when you tune up the constant beta E parameter. You see now there's even more mixing because of the coupling of the radiative transfer equation. So the addition of positrons, even though it might not have as pronounced effect on the total intensity pattern or just the colors, it affects the total amount of polarization, and it even affects the structure of the polarization. So why don't we add positrons now to our GRMHD simulation? Adding this with the R beta model, we see an interesting behavior. So we are trying to emulate the M87 in the R beta model, but here's with no positrons. So the circular polarization degree is actually in absolute value relatively high. But add positrons throughout each frame, and you see the circular polarization degrees decreasing in magnitude. That's because when there's intrinsic circular polarization governing these images, that the positrons cancel out the circular polarization from the electrons. They just rotate in opposite sense around magnetic field lines as the electrons do, and thus they send out light that is circularly polarized in the opposite way. And this is only in the MAD simulations that we observe this type of effect, because the MAD simulations have certain times. So these are different times. So one is different models at some simulation time 25,000 M, and another's at the dotted lines there are 30,000 M. At certain times, the MAD simulations, we find that they're dominated by intrinsic circular polarization. And that's the type of polarization that's not due to the Faraday effects. And at these times, you see the V over I behaves linearly in all these different models. However, at a different time, we find that that's not the case. So what distinguishes the times that look like they're monotonically decreasing magnitude of V over I versus not? Well, it turns out that the times that look like this are times when there's a rapid increase in magnetic flux phi in the simulation and a rapid decrease in the mass accretion rate, m dot. So we can actually predict when the intrinsic circular polarization is going to dominate the MAD case. And in these simulation timescale, as my master student Haley West is investigating, we can explain phenomenologically why certain times you get a canceling of the intrinsic circular polarization with positrons, and other times it's just dominated by the Faraday effects. So what does this look like in practice? So in the same simulations, we can look at these different times, and the morphology doesn't change very much in the total intensity with electric vector polarization angles or with the circular polarization maps. However, if you look at the different times with the MAD simulations, there's a big difference between times like these, like 20,000, 30,000, when there is non-monotonic change in V over I with positron fraction, and a time like this. This is one of the times in the previous slide where the V over I behaves roughly monotonic when you change the positron fraction. This is due to when you have the flux eruption event here causing a lot of intrinsic circular polarization. So it's very interesting that we can tie together a very peculiar behavior of roughly canceling linear polarization between the positrons and electrons with a particular morphological feature of the simulation. So this is the power of the observing job simulations, even after the data was available and even after images were available. To understand what's underlying the images, we actually had to take a deeper look and do this type of analysis and see what is causing some of the properties in these. So previously, in the old analysis that's is on the EHT collaboration papers, there was a very strong preference for the MAD models with respect to these observations, like the net linear polarization MNet. Here I'm taking this with different positron fractions and in different models, and with different sane versus MAD cases. So there was a MAD was the preferred model by far in both the MNet or unresolved linear polarization and the resolved linear polarization observations. However, you see that this table is roughly split between sanes and MADs in terms of the median model or the median time model value at these different types of phenomenologies. It turns out that the sanes are actually preferred when you look at the resolved polarization constraint, but the MADs tend to be preferred when you look at the global linear polarization constraint because the MADs actually have more symmetry. So it's not as clear-cut case if you don't include the positron effects and if you don't do this analysis with a fairly representative sample of models in sane and MAD cases. So even after you get a particular answer doing a particular analysis, it's worth using these observing job simulations to redo it. So this is work that's as my PhD student Joaquin Duran is helpful for. And also other PhD students in my group are helping to reverse engineer these structures when we include dark matter particles like axions that can also change the shape of the electric vector polarization angle pattern in a time-dependent way. So Yifan Chen has pioneered this, but members of my group are trying to replicate this. Now, let's see what the summary of this observing job simulations is doing. We have a very well-known observation now of M87 in full Stokes, but the models that we use after this image came out show that the MAD case has a roughly linear dependence of V over I at certain times when the intrinsic circular polarization is dominating when you're varying the positrons. And the sane cases don't show that behavior. They just show helter-skelter electric vector polarization angle rotation due to Faraday effects. And their densities are doing much of the work that the magnetic fields are doing in the MAD case in producing the total intensity. So the MADs are more likely to satisfy the net linear polarization constraints. However, the sanes are more likely to satisfy the sane polarization constraints. And here's a MAD case that looks like this intrinsic circular polarization dominated case. And here's what the sanes do. The sane simulations have a very different variation. Oops. Yeah, so you can even hope that this movie isn't distracting. So yeah, the sane has a different variation. Now, let's actually look at what the impacts of these images are. So now you saw under the hood, so how the sausage is made. How about looking at what the impact it's had been? So this image actually is very iconic. It's been estimated to have been seen by 4 billion people. If you look at JCAP journal, they estimate the impact of communication in astronomy. And this iconic image made the rounds in 2019 all over the world. And the circular polarization case, which I argue is actually even more informative from the astrophysical standpoint, because it lends credence to that picture of that Blanford-Knobloch jet where the vertical flux was actually being twisted up by the magnetic field lines. This picture, I'm hoping is going to get some more fanfare, but the linear polarization was taken in 2021, circular polarization was taken in 2024. So you can see that the CAP journal, or JCAP, has really estimated that a lot of people have seen the image, so roughly half of the world's population at that time. And this has made the rounds because it's a truly international effort. There's newspapers from Spain to Germany to England to Netherlands, which played an outsized role, Poland, all over the world. We really needed the entire world to serve as our collecting dish. So this is a symbol of what international cooperation can bring. So let's hope that we see more of this in the news than what we're seeing right now. And the first image of our black hole, so it's a fortuitous coincidence that the second black hole observed was the black hole that happens to reside in our galactic center. So that led the outreach to be very pronounced for the Sagittarius A star results, even though it came after the M87 result. It was from the same campaign as from M87 in 2017 in April, but the data for Sagittarius A star was harder to produce an image from because of the higher variability and the greater scattering in the galactic plane. However, this image should be astonishing to you because, as we've shown before, we're looking edge on into the galactic disk. So we're sitting in the galactic plane, but we see something that looks like it's looking at us face on the galactic center. So is this a mysterious property of the universe that all black holes point towards Earth, even though we're sitting edge on with respect to the large-scale disk? Who knows? We just need to look at more black holes in order to see this. So this made the astronomy picture of the day when we saw Sagittarius A star polarization. So again, we're hoping to make these images even more iconic throughout. And what's in the future? Well, we have 345 gigahertz images and beyond. So right now, these are not images, but these are the first fringes that we got by doing the same type of experiment. But now we need even a longer baselines to get to 345 gigahertz. So we need to take the correlated flux at our astonishing frequency, 345 billion hertz, and correlate them all over the world on the largest baselines in order to see structure at 345 gigahertz. And this will get even better when we go into space with space-based very long baseline interferometry. So where the preliminary structures we're seeing, again, they're ring shapes of the same structure, of the same sources that we've been seeing. So Sagittarius A star, we see some scattering effects as well. But at 345 gigahertz, we could actually penetrate the scattering screen even better. So we're going to see the sharpest images ever when we move to 345 gigahertz and beyond. So can we learn anything from the theoretical standpoint as well? Well, we can use that same exercise when we did the emission models like the constant beta E model, which was the magnetic fields directly feed the particles that are radiating. And we can see whether the bilateral asymmetry, when you add positrons, you get the more bilateral asymmetry in these models, whether that corresponds to different observations we see in space, like at 3.679, where we see it on scales that are further than EHT, and we go down to the EHT scale, we see the persistent bilateral asymmetry. Could it be that some positrons are adding to this or subtracting from it in different parts of the structures that we've seen at different wavelengths? Possibly. So if you want to get to more exotic physics, my Rice PhD student, slash co-PhD student, slash mentee, Deshaun Jones, is working on what happens when you do the emission modeling with the EHT, but now you add in hotspots. And if you add in these hotspots, you can test whether time delays around the black hole are being due to to the image being multiply lensed by light going around the black hole several times. And you can see these features in the light curves, whereas you had a primary feature of a hotspot, possibly from behind, being followed by another being lagged in time by another feature that's a secondary feature due to rotating around the black hole several times. So I'm going to leave you my conclusions. Scientifically, we turned the Earth into a collection dish at 230 gigahertz, confirmed some of Einstein's general theory of relativity, and we've seen that all black holes so far point to Earth. Remarkable. It's very coincidental that both of these images were face on, as we found with our galactic center dish. We observe JAB simulations, which is what my group in UTSA and in part Rice specialized in, to link intuitive electron-positron models to the turbulent heating physics that seems to work best in AGN like Sagittarius A star, and also to see whether positrons could partially be responsible for the electric vector polarization patterns we see. And for Sagittarius A star, we saw that we can break up the phenomenology into a few categories of magnetic to particle energy conversion models that don't fit the observations, but some models that are compact and asymmetric, highly variable, that fit the observations with the high F and beta crit regime. So the inclination effects are strong, and before we did this blind, we saw some of the features of the hotspots when we took it at intermediate or roughly face-on inclinations. For M87, we did this polarized emission modeling between 43 gigahertz and 230 gigahertz with both the jet and the inner horizon features. And we saw that the observations favor a Blanford-Knotcheck jet, namely the spiral electric vector polarization structure, signaled vertical magnetic fields, piling on to a rotating black hole, and that rotating black hole sourced this Blanford-Knotcheck jet that we see in all of the observations. However, it's not clear what the role of positrons is and how sane or mad the flow is, and that's a subject to be investigated with my group or yours. So the outreach consequences, we saw the first black hole images in M87, and we saw our black hole in the galactic central Sagittarius A star. These are going to be iconic fixtures in your 21st century astronomy books at some point. We saw that these models were consistent with relativity thus far, but what happens if we see another black hole that happens not to point straight to Earth and has different lensing features and looks completely different as some of those rejected models in the Sagittarius A star investigation? The EHT has resolved the first structure at both 230 gigahertz and 345 gigahertz, so expect even sharper black hole images, and we're poised to take the first black hole movies. Stay tuned. Thank you. So any questions?
Yeah, I had one in the chat, but I'll go ahead and.
Oh, I didn't. Oh, sorry. Yeah, yeah.
Are there any plans to launch satellites to do the same kind of imaging where, you talk about having stations on Earth based. If you put them in outer space in a high orbit, you could even increase your aperture, basically your effective aperture.
Great question. So that depends on the funding climate, of course, but we certainly have proposals where we have the technology to do it. So there's the Black Hole Explorer BEX, which might be online in 2030, barring catastrophic cuts to funding, which we don't know right now. But the BEX Explorer will potentially put satellites in low Earth orbit and increase the coverage and the resolution tremendously. But we really need to hold strong in our sciences and keep the curiosity and the support going, because really it's highly funding dependent.
Yeah.
What are you proposing as the source of the positrons?
Yes, so that's another good question. There are processes where you can have lower energy photons coming from the surrounding accretion disk interact with Comptonized clouds or in portions of the jet funnel. And you can have the so-called Bright-Wheeler process, which is gamma gammas or two energetic photons in a certain frame turn into an electron-positron pair. So you could have that Bright-Wheeler process going on in the funnel of the relativistic outflow, or you can have so-called spark gap processes right above the pole of the black hole. And those processes happen when you have an outflowing jet of plasma in the already low density jet region being next to a charged starved region below which plasma goes directly into the black hole. So if you have a charged starved region due to the geometry and the effective torques and centrifugal forces of these relativistic jets, these charged starved regions have very, very large electric fields in sources like M87 because the potential difference is very large, the fields are very large, and you can accelerate particles that end up producing these pair cascades in these charged starved regions. So the density of the jet region is already low, so it's possible that the pairs in these spark gaps are a depreciable fraction of the plasma in the jet.
One other question. You showed one time difference in temperatures between electrons and protons. And how do you account for them not being in equilibrium?
Yeah, so this is exactly what the art of observing JAB simulations is. So these are two temperature simulations, at least. So if you have an electron species that's evolved in your simulation, you can have the electrons cool through synchrotron cooling way more efficiently. So you have this process becoming a lot more, so the reason why the electron temperature models were suppressing the electron temperature at high betas is because we're giving the phenomenological behavior of synchrotron cooling or other types of cooling, maybe inverse Compton cooling. But there's because the formula for synchrotron radiation has a dependence on the charge mass ratio squared, it turns out that it's just a lot more efficient to radiate if you're an electron than if you're a proton. So there's a two temperature assumption that's built into a lot of these simulations and into the semi-analytic models and the analytic models. So Stephen, you're muted if you're talking.
There we go. Sorry about that. So I put a question in the chat, whether or not you agree with the opinion by Dr. Roy Kerr of the University of Canterbury, where he is basically saying that this whole theory about singularities and black holes is just dogma. And he disagrees with the relativists who suggest otherwise, and he does it with some, I don't know, for a physics paper, I would say rather strong language, calling it dogma, and says, quote, "When theory predicts singularities, the theory is wrong!" Exclamation.
Well, I'm sure that
what your thoughts were.
Well, I mean, Mr. Kerr is a highly esteemed, highly decorated scientist in our field, and came with the metric whose name, the Kerr metric, bears his imprint. But perhaps this is strongly worded, especially in view of the fact that at least the horizon part, the Event Horizon Telescope is directly observing a horizon. I mean, there are models where we put in surfaces with different albedo or different reflectivity than a hole, effectively. It seems like a lot of those models are highly inconsistent with an image like this. So the fact that there is a horizon, the fact that there is a hole, whereas almost any central source that we're seeing out of radiation coming from prior to getting to the critical density you need to collapse into a black hole didn't look like this, and now you have a completely different morphology that's really consistent with the size of the Kerr metric predicted by Einstein. It gives credence to at least the singularity in the Kerr metric that corresponds to the horizon. What happens with singularities is something that the EHT hasn't really opined on, and I haven't opined on to such a large extent. The singularities are, again, we can say that because the perihelion precession of Mercury, Mercury is doing like this and like this and like this in a tiny, tiny, tiny fashion, it's not a perfect ellipse. We can say Kepler's laws are wrong, we can say Newtonian gravity is wrong because of this tiny correction, or we can just say it's correct to the correspondence limit in that things behave, unless you have exceedingly precise astronomical measuring instrument to actually measure the deviations from Newtonian gravity. Newtonian gravity is right to that correspondence limit, and that's a notion that's coined by Roy Kerr. Coined by Niels Bohr. However, with the singularities, the geometry of black holes is highly consistent with having the surface gravity of black holes approximate much more the geometry of our throat. The throat is basically, from the outside of the black hole, it's the beginning of what would eventually be the infinite singularity. So if you have smaller and smaller black holes having their exterior geometry look more like the geometry of our throat, you can say that to a correspondence limit for black holes of all sizes that we've measured, it looks like their effect of the space-time is converging to the effect of what it would be if they were a singularity and the throat were infinite. So to a correspondence limit, we've observed that the smaller the black hole, the greater the surface gravity, and the closer you get from the horizon to the purported singularity, the more the exterior geometry behaves like a throat. So you can say to a limit, it appears that the black holes at least become more throat-like the smaller the horizons are, but we haven't observed a singularity.
Thank you.
The images are stunning. It's mind-boggling. Now, my frame of reference here is from the standpoint of the astrophotography that we do. And we're taking visible light images, we're exposing very distant objects for a few hours and even up to 100 plus hours to get an image. And the longer we expose, the more detail we get. My question is there an analogy to what you do? It seems like the signal you're trying to pick up has got to be incredibly weak. How long does it take? How long do you gather data at 345 gigahertz, for example, in order to be able to input that data into your processing and end up with an image?
Well, the longer the better. So we've shown the first time that we were confident enough that we had enough exposure, namely those 4 days in 2017, we had enough data to produce the structure, at least in the total intensity that you see here. Of course, the longer the better. The more baselines, the better. The more coverage in UV space, the better. So it's really just a matter of whether you want to look like the photon rings in Interstellar, whether you want to, actually, let me use slideshow. Whether you want to look like, if you want to look like this, if you want to look like, if you want to look like this, it's going to take way longer and with way more coverage than if you just want to look like this. So if you want to look at what we've done, it's basically, those 4 days in 2017. But we have other campaigns in other years where we see the ring position of the hot spots or bright spots in different places to roughly similar levels of precision. But we also see images, or at least structures, if they're not images yet, at 345 gigahertz. And the more coverage we get there, the better they're going to go. So it really just depends qualitatively. If you want to get much sharper than this, you need more time, you need more baselines as well. But if you just could see that you can do science with this, then 4 days in a year might be enough.
Thanks. Oh, yeah, no.
Well, thank you so much, Dr. Anantua. I appreciate your time. and your insight in all this. And yeah, we just really appreciate it.
Yeah, thanks a lot for the great questions. Everyone, asked very, very advanced questions, and yeah, it's great doing this. Yeah, I hope to see the recording and future versions of this. And I understand that you might even have my postdoc come here in a few weeks. So stay tuned for part 2 if you want.
Thanks, sir.
All right, so I'm just going to leave the Zoom, or? All right, I'll leave the Zoom.
Oh, yeah. 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 So we're gonna do a 10-minute 10-minute break to recover, and we'll see you in 10 minutes. Watch your eyes.
Well, one thing our speaker missed is that when you take a break for 10 minutes, it goes into 15 or 20. Yep. Okay, so let's get started with the raffle. There's several new books here to be seen, some picture books that are pretty good, through the Apollo Earth mission to a brief history of black holes, so you can refresh yourself on what you just heard earlier. And so going back to our founder, Mary Noble, she created, it's amazing how much astronomy has changed over the 76 years. Pretty fascinating. And if you're interested in change over time, here are Sky and Telescopes magazines from 1940s to 1990s. So if you want to catch up on 50 years of astronomy history, this is part of the... That's right. So you have the knowledge base in your hand here. Oh, you are? Okay. So are we ready here? Oh, already. Apparently this is a new random way of doing it. Yes. So the tickets have already been drawn. So the first winning ticket is 4806778. So everybody check 4806778. I knew you did. Okay, the next winning number is 4806799. And we'll keep this train moving. 4806754. 4806754. Okay. Slightly down a little bit, 4806728. Last three digits, 728. And the final number, 4806739. 739. Sure. Ooh, no one had that? 739? Check again. 4806739. All right. That's mine. Yeah.
Oh, and that'll be the last time I open a presentation with a corny joke. You guys are a hard room, tough room. What's in the sky? So, right now I'm going to tell you about everything that's happening above the clouds in our sky from March to April.
Check one.
Okay. Nice. Yeah, and it looks like it's not blinking. All right, yes. For Christian. All right, so there were a fortunate few that saw the total lunar eclipse. What was it, last week? And these are some pictures of it. Next slide. Got some really good shots in here. I like the progressive one. What is that? Was that Jim Potts? Yeah. Real nice. All these beautiful color too. All right, next slide. All right, autumn on Saturn. So I'm here to tell you that when a planet is 15 degrees away from the sun, forget about it. I tried. I played hooky from work, and I tried. I had my C11 set up. I had it right on Saturn, and I knew it was there because it was a little squishy thing in my view. And yeah, it's no good. Backslide, please. Now, and then of course Saturn's in conjunction with the Sun, so you've got if you want to look for Saturn while it's in conjunction with the Sun, it'll be your second to last time to see anything. And then you're like, well, let me give this another shot, and that will be your last time to see anything. So don't do that. So the date of the ring crossing is March 23rd, so it is nigh, and the rings are unlit for 44 days, okay? And I'm not really sure why this is the case, unless it's like it goes to, it goes to plane on us, and it goes just a little bit the other way, and then it comes back. But that's what we got going on here, is that on November 23rd, the rings go edge on again. And it's about 7 weeks, 7 weeks past opposition, so it's going to be in the middle of the night. So we've got an opportunity to see this really cool thing. I've never seen it in the eyepiece before, but I'm pretty excited about it. Next slide. This thing hadn't blown up yet, so heads up. Next slide. There you go. That's the spirit. It's optimism right there. So the last of the transit season with 2 moons, shadows on Jupiter is here on March 19th. That's tomorrow. Well, that's morning. That's tomorrow morning. So Europa and Ganymede, if you're up and doing that sort of thing. So next slide. Next new moon is on Saturday, March 29th. And next slide. Hold it. Oh, well, March 29th. What is that, Saturday? That's, yeah. So anyway, so what all is happening during new moon? So we got a partial solar eclipse. It's going to be visible at the most in eastern Canada, but and it's in the morning. It's in the middle of the night. 3:50 a.m. Central Time. For anybody that's online or in eastern Canada. Next slide. What we've got is 3 pretty good places on YouTube. And of course, I'll be putting this in PDF and putting it on the Groups IO site, so that or you can just Google, partial solar eclipse 2025. But these are some good places where they're going to actually be broadcasting it live and doing some commentary and talking about it and stuff. Next slide. This is what is the Messier Marathon. So wonderfully on the new moon night at a rising star. If you haven't heard about it, here we go. Chance to possibly see all 110 Messier objects in the sky over a single night. Things include me doing introduction to solar observing. I'll have I'll have my telescopes out there with white light and hydrogen alpha. Brandon Hamill is going to do, sir? And Danny Arthur. Who? Oh, Brandon Hamill and Danny Arthur doing Star Hopping, the original Go-To. Very cool. And Robert Serkis is going to do Introduction to Image Capture, and Stephen Kennedy is going to do a thing about polar alignment. So in his slide, he's going to talk about later on this evening, he'll have the times for when those things are happening. And if you can't make this thing, then Chris is going to be broadcasting the Messier Marathon using our new Noble Observatory, which you're going to hear about a little bit later. Next slide. And the full moon is on Saturday, April 12th. Next slide. So I'm going to spin through this real quick because I know that we've got meeting to do. But what I want to feature is I want to feature the little kitty. This is Leo Minor. It was one of the few that are still in existence, the constellations that Johannes Hevelius came up with in 1687. And there's 3 stars in it with planets, 2 formally named stars. It's the little guy right above Leo in the sky. So, oh, good Lord, I had Leo right here. Leo Minor's up here. Wow, nice. Anyway, so that's how insignificant it is in the sky. It didn't even make it into the frame. Next slide. So the first object is called Hannes Voorwerp. Voorwerp is Dutch for object. But this is a school teacher that was participating in the Galaxy Zoo project, which is a citizen scientist program that's been going on for quite a while. And what she discovered was a black hole, in the theme of the evening, a black hole turned on, and as a quasar, shot a beam of light through this 300,000 light year long just tidal spread of gas that was coming off of a galaxy, likely a remnant of a galactic collision, and it lit up a part of it. It's a cone of light that energized, ionized this gas there. And they didn't know what the object was, and when she found this, they gained insight as to what was going on here. So that's, next slide here. And this is actually the lit up portion. So this thing is 300,000. It's much more than this, but it's basically as if this quasar basically shined a flashlight on this portion of this long tidal tail. And so that's pretty crazy. So next slide. So in the Halton ARP catalog, which is all peculiar and irregular galaxies, most of them things like galactic collisions and stuff like that. We've got ARP 107, and it's a merging pair of one spiral and an elliptical. And what scientists think is that the elliptical basically passed through the spiral and really goofed it up. Next slide. So here's the elliptical, and here's kind of what's left of the spiral. And it basically ended up with this long extended arm and this massive tidal tail that basically bridges the two galaxies. And in addition to that, it actually, no, that's another object. Next slide. Then there's NGC 3432. So this is known as the knitting needle galaxy because they're always making stuff up with the names. It's also known as ARP 206. It is a spiral galaxy that is interacting with the dwarf galaxy. And in the year 2000, if anybody's familiar with Eta Carinae, It's that, I probably should have put a picture up here, but it's an exploding star as nova. This is the nova that exploded and was found in 2000, the light finally reached us in 2000, was of the intensity that made scientists think that this was a supernova exploding. But it was just a little bit weaker than a supernova. It was just an extremely highly intense nova. And it's got the classification of a supernova imposter. Next slide. And this is the galaxy that it's in. There's your dwarf, and this is spiral galaxy such as it is. Next slide. And there's NGC 3344, known as the sliced onion galaxy, and it's about half the size of the Milky Way. Next slide here. So this is actually a picture from David Cox. It's one of his earlier pictures, and what scientists have identified about this is that the inner core of stars is not influencing the outer ring of stars. And so this is actually another clue that this galaxy underwent galactic collision. You know, there's a lot of different things, the middle of the galaxy is tilted one way and the outside of the galaxy is tilted another, like Deerlick Galaxy. And there are a few other things that leave clues that a galactic collision took place. So that's kind of the clue with this one. So next slide. NGC 2859. This is actually a rare galaxy. If you go to the next slide here, this is a Hubble picture. This is not something that you'll see in your telescope eyepiece or anything. Well, you could. I mean, it's not teeny tiny. Those are minutes, not seconds. So yeah, that's not bad. The weird one about this is the fact that, you've heard of barred spiral galaxies. Well, this actually has a secondary bar that's almost at a 90-degree angle from the primary bar. Now, barred galaxies, like about 2/3 of spiral galaxies are barred galaxies. It's actually a part of the evolution of a galaxy, a little more towards the youth end of things. The scientists actually think that this secondary bar is actually a result, possibly a combination, of resonance and the funneling of the gas and stars through the primary bar, because that's an effect, a gravitational effect that a bar has in a barred spiral, is this funneling of gas towards its center. So, and on top of that, there's actually a detached outer ring. So it's actually a really interesting galaxy. Next slide. Yep, and so here's some things. This one right here, esahubble.org. This particular article right here was really actually quite interesting about one of the objects I've got in there. And of course, my other sources here. Next slide. So the picture I want to feature here is by Christopher Ashford. This is Orion's belt. Very, very nice. Let me see what we got here. 1, 2, 3. And the belt right there. So thank you very much, and keep looking up. Do we want to have lights on or off for the rest of this? Leave them off for now? Okay.
We're getting the points of the announcements and the monthly reports, so if you're on this list, please make your way forward. Patrick, you're up first, so hand the mic over to you.
All right, do we have the slide for the star parties? Let's go.
All right, Bob, you're up.
Okay. Something exciting for me is this is the first light of the Noble Observatory. This was taken Sunday night. It's 40 minutes total of the Rosette Nebula, the one-shot color camera. Ordinarily, I chose this image simply because it fills the entire field of view. Ordinarily, I would do this as a mosaic. So why is this a big deal? If you've been out to Rising Star, all you've seen is a dome with a really ugly cover on it. And this past weekend, Jim and Catherine and I, next slide, please. Finished it out. We're in the 85-15 rule. The mount is the CEM 60. It's a Raza 8 with a 183 MC color on it, and it can be run remotely. So that's really cool. There's something else I was going to say. So right now, we have to manually rotate the dome, and we have to manually open the shutter. And we're going to be working on getting that automated over the next few weeks. We've got a small group selected to hash out procedures on how to use the equipment. And the hope is in May, we'll do a presentation on a walking tour and how we use it and what we plan to do with it. So it's just awesome. I can tell you I'm super, ordinarily, raise your hand if you're super excited about doing polar alignment. I was Sunday because we're able to get that, and the polar alignment is within 10 arc seconds of the celestial pole, and the guiding was 0.12 RMS. That's pretty damn good. So I'm super excited, but I just wanted to let everybody know. Oh, okay. So tomorrow I'll be sending another email out about the Messier Marathon with more opportunities to register. We've got about 50 people signed up already. It's scheduled for March 29th, and not sure when we're going to open up the field, but Bill's going to do his solar presentation at 3:30. At 5 o'clock, I'll start an introduction to image capture on, you guessed it, the Noble. And I'm really looking forward to Stephen's hints and tricks for polar alignment, because he's going to show us how to get a pretty good polar alignment in the daytime and then fine-tuning it after dark. And then Danny Arthur and Brandon Hamill will talk to us about star hopping, the original go-to. And then the Messier Marathon will begin around 7:45 as soon as the sun sets and the people with really good eyes can see the stars. So I hope everybody can join us. Any questions? Thank you. I'm really organized. So, there is another one. Yeah. So everybody's welcome. You're welcome to bring up to 10 guests. There are limited slots for RVs, and we'd like to know if you plan to leave before 12, before 2 or stay overnight. And we will be live streaming, and volunteers are welcome. And we have several that have already signed up, and I appreciate that. Again, that's where you register, but there'll be an email coming out from Night Sky Network tomorrow. And again, thank you.
Okay, let's move on to the outreach reports.
All right, so as you saw on my email earlier, we do have a couple this week. I got one for the city of Bedford. They usually have a camp out. We've done this before. It's a nice little location. Now it starts at 6, but we wouldn't have to show up there till close to sundown. I'm not going to be able to make that one, so we can just get a couple of scopes. Please let me know. Appreciate it. And then Saturday will be our first Dinosaur Valley Star Party of the year. There's the address there. We'll be setting up in the main overflow parking just past the main tracks. If you have any questions, just let me know. Next slide. Okay, this one on the 24th, this may not actually happen, so I'll let you know on that. And then on the 5th, I know this is also the night of Tandy Hills, but there's also a Cub Scout that'd like a few scopes. I'm going to be there, so maybe one more scope. If not, I can handle that, no big deal. And see if there's anything else. And then we got another camp out. This one is Lynn Creek Park, basically by Joe Pool Lake on the 12th. So again, I'll put the rest of these on the group as we get closer. Thanks.
Thank you.
Well, our 2025 season for Tandy Hill Star Parties didn't start out very well with the rain out. We're going to try again April 5th. And the sunset's around 7:38, something like that. We won't have all the planets like we did or would have had on the 8th, but we will still have a couple bright ones, Jupiter and Mars, plus, of course, the moon. It's always a good time for people that have scopes that don't know how to use them or need help with them, or people that are looking for scopes to come on out. It's so bright out there with the surrounding lights that dark sky protocol is not really absolutely required out there. So if you fit those categories, come on out. We'll be glad to help you. That's April 5th, and sunset's about 7:38, somewhere around there.
All right, young astronomers, we're still working out changing the young astronomers from a Tuesday night, because that's a school night, to the fourth Friday of the month. So hopefully we'll get that figured out for April. So nothing in March right now, but that's what we're working on right now. Thank you.
Good evening. Well, I guess I'm a three-ring tonight. So we have 3 scheduled 1687 Foundation events upcoming. We had one 2 weeks ago. It was an extraordinary event. It was for young people that had epilepsy, and I really enjoy these events. So I was there too, and the excitement of people who ordinarily never get a chance to look through an eyepiece is phenomenal. A lot of oohs and ahs, and just tremendous amount of excitement. We had 31 guests. We had 31 guests. We had about 31 guests on that evening. This coming Saturday is for sight-impaired veterans. Si's leading the cadre for that. And then on the 5th, it sounds like we're going to be really busy on the 5th. We have Grace After Fire Veterans Retreat. And then Friday the 9th, it's for a group called the Open Door Staff. I haven't got all the details on that yet. And ordinarily, we don't do things on the Fridays. We use Fridays as a backup, but on the one in May, that's just the schedule. So I'll just hand it over to Si.
Yeah, so we got 5 people for this weekend. That's great. we're going to be having a sign up online for the next two, but we got a good representation for this weekend. So love to have you all come out sometime. We reimburse your gas. We get a $50 reimbursement for traveling out there. So look forward to seeing some of you out there sometime.
Great, thank you, Si.
All right, Rising Star, I think you've already heard a lot about it. Congratulations, Robert, on getting that Noble Observatory up and running. It'll be fun to see through that. I do know that Tom and Charlie and Bruce have been working on starting to get the ventilation in the large container. That project should finish up later this week. And I believe the next plan is to work on a partition between the two sleeping quarters. And that will be another week or two down the road. Is that correct? Okay. Yeah, okay.
The state park is now probably going to do a soft opening this fall, hopefully. Everything's under construction. There's a lot of trail clearing going on to make it more aesthetically pleasing. So if you want to volunteer, there's work parties on Friday and Saturdays. I believe through April you can sign up through the Facebook. Nazarene's volunteered. I think Mark's volunteered. Michelle and I went out there. It's very picturesque. It's going to be a good park. It's 4 hours of labor. It's hard work, but it's worth it. And everything's looking good in that direction. So.
Thank you, Tom. All right, so just a brief update on the Cross Plains Public Library outreach. We had our last outreach event in February where we did a binocular discussion. And the next plan is to have a star party for them, but the goal is to have a variety of telescopes out there so they can see the various types and sizes to help them make a decision if they want to buy a telescope. They enjoy, like most people, looking at the night sky, so that's just a good opportunity to do that. Three people have submitted applications from the Cross Plains area to become members, and as far as I know, 2 people have paid their fees, paid their dues. So we're at 2 right now, with one on deck. Thank you. And George, are you online for the website and media? While he tries to open his mic, if he's not online. We'd like to say that we need to do an update on the frequently asked questions, or I think that's what it is, FAQ. It's slightly out of date. I will be reaching out for people to review each of those FAQs and bring them into the 21st century. We're also going to make an effort to put our pictures into that website and do away with any stock photos or any other perhaps copyrighted photos that might be out there. But we've got the telescope, so I think we can make this happen. Okay, so we can just skip that and go to the next item. Do you want the lights on or off?
Thank you, Bruce. Good evening. My name is Constantine, and as your treasurer, I'll be offering 2 pieces of information today. Of course, the typical monthly report, but I also have the year-end 2024 summary. But before we get started, I want to clarify something. For those of you that noticed that I'm dressed like our president, Bruce, I am not vying for his position. So let's go ahead and take a look at what are we doing first. The year-end summary. Do you have the table that goes with that? Terrific. Okay. So our bylaws require each year that we do an internal examination. This is basically an audit. And our treasurer, our secretary, Robin, as well as Tom, Roth, and Bruce, got together and went through the documentation, which included the monthly bank statements, receipts that we had, our check register, and all the records available to try to confirm what's happened over the past year. And as you can see, it is a very unique year. If you look at the revenues for 22, 23, and 24, you'll notice that the total revenues for 24 are substantially higher than the previous years. Similarly, the expenses are also substantially higher than previous years. It's a very unique year. It basically encompassed the development of Rising Star. This is why everything is so skewed. For the first time in the club history, as far as I know, our revenues were over $50,000, which puts us in a different IRS category. However, we were lucky enough that there's some verbiage that says if this is a unique situation and your last 3 years are less than $50,000, then you don't have to fall into that category. So we're able to complete our IRS reporting as we have on previous years. Let's go ahead and go to the next slide, please. This is a graph of our revenues, a total of $64,000 as previously mentioned, but I wanted to highlight for you a couple of things. Take a look at where our income came from. Typically, it's from members and new members, as well as a few donations. But this past year, as you can see, there's a substantial amount of money that came from the 1687 Foundation, and that's going towards paying off our loan for the development of Rising Star. Take a look at donations. We had a good amount of donations, but also a number that were designated specifically for Rising Star. Also had some good income from our pad leases. Any questions on this? Let's go ahead and move to the next graph, which is our expenses. And oh my gosh, take a look at that. 75% Rising Star development, a very unique year. I don't expect 2025 will be similar. But you can see everything else kind of falls in place. We do have some new expenses starting this year, starting last year and extending through this year, and that is we do have internet out at the Rising Star, which will be a monthly cost, electric power at Rising Star, which will be a monthly cost, and that's in addition, of course, to our typical monthly costs for Zoom and other such things. One thing that has dropped off is the storage building. We no longer have to pay a lease on that. Any questions on this? Please know that this summary, if you want to look at it in more detail, is available on eGroups. Let's take a look at where we are on our monthly report. It's been a fairly quiet past month. We started our last report at $38.9 thousand. We had income of $240 and a donation of $80 and total expenses of $209. So we're sitting right now at $39,000 and something. The Rising Star Development Fund on the bottom half of the page remains unchanged for this January, February, and March. However, starting this next month, we do anticipate our first income, which is expected any day for the first Star Party that occurred out there. And then there'll be a little bit more phase 2 work that's going to happen, and we'll be making our second principal payment and first interest payment on the loan in April and May. So more detail on that to follow. Any comments or questions? Well, thank you very much.
Thank you.
We have an update on our trademark, and I'll let Stephen Kennedy talk about that.
Thank you, Cy. I'm pleased to report to everybody that I've been able to confirm that just as in physics, where there is this thing called singularity, which is a region of infinite density and gravity where the laws of physics as we know them break down, we have something very similar in the law. It's called the United States Patent and Trademark Office. It is definitely a region of infinite density, only it's the law of logic that breaks down. And I have a good example of that. We got a response from the trademark office to our very basic trademark application covering our logo. And I got 2 questions in response to our application. The first question is, do we claim exclusive rights to the words Fort Worth? No, we do not claim. We have a trademark on the words Fort Worth. So that's one question I have answered as part of my response to the office action. And the second one wasn't quite so dense or illogical. They asked us whether or not color was an essential item in our, an essential feature of our trademark. And since we might want to change the colors from purple, black, and white in the future, the answer is no. Color is not an essential feature of the trademark. So I responded to the office action by disclaiming the words Fort Worth. We're not going to claim that as a trademark. It's just Fort Worth Astronomical Society when used with the logo. Color is not an essential item, so we can change the colors. I have submitted that earlier this evening, so our trademark application should be approved because they had no other objections to it. Our trademark our trademark application on the logo should be approved very soon. I would expect it's going to be perhaps early summer or early fall, that it will be, late summer, early fall before it is officially approved. So that's my report.
All right, thanks, Stephen. We have no other legal updates for right now.
Thank you, Cy. Can you get the lights? So in terms of the other business, I did have one thing to report, and that has to do with our outreach activities. So many people in the club spend time and effort going into the to outreach parties, either public schools, private schools, just a number of things. But sometimes the schools send us a letter. And I want to read one letter we got from the Springtown, wait a second, got to get this right. From the Springtown Elementary School. Just wanted to say a word of thanks. Thank you for hosting a stargazing party at Springtown Elementary School. We appreciate your knowledge and generosity in sharing the wonders of the night sky with our students. Sincerely, Amberly, the principal. So, someone took time out of their busy day, especially in a school district, administrator, to recognize the effort that the people from this club did at the Springtown Elementary School. So I just wanted to tip my hat to them. All right, I think we're going on to the next slide, which will be upcoming events, upcoming speakers.
All right, so we've got the Solar Dynamics Observatory, otherwise known as SDO. This is a telescope that's in orbit out in space. Well, or else would it be? Sorry, long week. Dr. Dean Pesnell is going to be joining us, and looking very forward to that. Oh, sure. Also, beer. So there's a group of us that get together at the Social House, which is just down the street, and yeah, it's a lot of fun.
So that brings us to the end of our tonight's general meeting. Thank you all for coming, and I hope you have a safe drive home as you work out your way outside this maze. Good night.